So in the last video, I computed two different integrals involving a vector field and a region with boundary C. So on one hand, I computed this difference of partial derivatives of the vector field's component functions across the region. And then on the other hand, I computed a line integral of the vector field along the boundary of that region. I want to say a word of notation before moving on to the second part of Green's theorem and then actually proving Green's theorem for you. And that is that, a line integral of a vector field along a curve is computed through a parameterization like this, and I can observe that that computation is exactly these two line integrals with respect to x and with respect to y, respectively, added together. And that's because the dx is x prime of t dt, and dy is y prime of t dt. And when you compute this dot product, the component functions of f being m and n produce exactly those two line integrals. I think I made that observation before, but typically we write such a sum like this with just one integral sign, and that's the integral that you see in Green's theorem. Okay, so more on this later, and then actually the interpretation of the quantities that these integrals are computing is going to be next section, so circulation and curl is later. Now it turns out that there is another version of Green's theorem. It's developed in the same theoretical manner as the first one, but it relates to integrals that measure some different quantities, flux and divergence. What it is the line integral, again, of some component functions of the vector field along a curve ends up coinciding with a double integral of some mixture of the partials integrated across the region that the curve encloses. So let me just, again for practice, crank through a double integral and a line integral, and we'll see that they give the same quantity. After going through all those examples, we're really motivated to use these theorems because in each case, the double integral ends up being a lot easier to compute than the line integral. So the theorem helps us compute circulation or flux without having to parameterize and do the awkward line integral. If the double integral ends up being easier, I know I get the same number anyway, so I may as well just do that. So that's the strength of these theorems. Okay, so here is a line integral, and I'm going to just compute it straight up directly, and then in part B, I'm going to use Green's theorem. What that means is I'm going to compute this double integral and see that it's easier. Okay, so part A, I'm going to compute the line integral directly, meaning that I have to parameterize the curve. In this case, it's the unit circle, counterclockwise. The standard parameterization of that is as follows. Okay, and now for the line integral. The circle there is just emphasizing that the curve that I'm integrating around is closed. Okay, so let me write these components off to the side so we can see them clearly. M is the x component function of the vector field, and I'm going to evaluate that at the parameterization. Okay, and then n is the y component of the vector field, evaluated at the parameterization, and then dy and dx are the differentials computed from the parameterization. So dx is negative sine t dt, and dy is cosine t dt. Okay, so this is the integral that I need to compute. You may remember from maybe Calc 2 that when you have sine or cosine raised to even powers, then you're going to want to use a half angle formula as many times as you need to reduce these down, or double angle formula, whatever you want to call it, to reduce these down to single powers of sines and cosines, but like double and quadruple angles. I'm just going to go ahead and look up the antiderivatives of these expressions because I don't really want to focus on integration techniques right now. So I'll write out the antiderivative of cosine of the fourth, then sine of the fourth, then sine squared. Okay, there it is. And if you want to verify that this is the antiderivative, knock yourself out. Just apply those trig identities and go to town. All of the sine and cosine terms here take the same value at 2 pi as they do at 0. So if I plug in 2 pi to all of them and then subtract what I get when I plug 0 into all of them, then they're all going to cancel out. So I'm not going to bother putting them in there. All that I really have here is how many t's total do I have? I have 3/4 and a half, which is 5/4 times 2 pi minus 5/4 times 0. So I've got 5/2 pi is the value of the integral. Okay, and later in the next section, I'll make the observation that this line integral computes what's called flux of the vector field across the curve. It's basically the flow of the field across the curve. All right, now Green's theorem tells me that if I don't like that computation, I can do something instead. And again, I'm just going through both halves of Green's theorem to demonstrate that you get the same thing, just practicing computing all these different kinds of line integrals. But usually, the use of Green's theorem is to save yourself some time. You're interested in what the flux is, and you're going to just do part B and get yourself the value in a little bit quicker way. Okay, so let's glance up here to see what Green's theorem tells us. Instead of computing the integral that I just computed, I can take the partial of m with respect to x and add it to the partial of n with respect to y and integrate over the region that's enclosed by the curve. Okay, so let me crank out those partials. So m is x cubed, so dm dx is 3x squared. dn dy is 3y squared plus 1. And the region over which I'm integrating is the unit circle, right? That's what the curve encloses. So I think I want to use polar coordinates to compute a double integral. Okay, let's go ahead and set it up. Okay, and you see that this double integral has given me the exact same answer as the previous integral. And I knew that that was going to happen because Green's theorem tells me that those two integrals are the same.